Greetings and salutations, YouTube. Japo here, and welcome to the second episode of the Tommy Project. This week, we're going to be tinkering around with really the only pieces of the robot's original circuitry I'm going to be keeping, the 1645 motor control ICs. Never before in my travels have I ever happened across the 1645, so as when faced with any mystery IC, the first thing we do is fire up ye olde Google machine and see what we can track down. Luckily enough, in the first couple results, I happened across this. This is the datasheet for the Sanyo LB1645 motor control IC, which looks close enough to what we're using. For those who have never read one of these things before, basically the datasheet gives us all of the information on the chip, what the various pins are, what it needs for input voltages, currents, all that fun stuff. Looking at the voltage requirements on the first page, however, it looks like the 6 volts used by the Omnibot to run its batteries are a little out of spec for this chip, but you know what? It worked fine, so YOLO. For our purposes today, the most important part of this datasheet is this. This is what's called a block diagram. Basically, it shows us what's going on in the IC, where all of the various pins connect to, and what they do. The first thing we notice when we look at this is the 1645 is basically an H-bridge. What an H-bridge does is it allows you to reverse the current flow on the output pins by setting the appropriate input pins. Another piece of useful information we find in the datasheet is this. This shows us a sample application circuit using the chip, which is very important so that we have something we can pretty much completely ignore. Based on what I saw in the block diagram and the sample application circuit and remembering how things looked before I desoldered everything, I fired up a copy of Fritzing and I came up with this. One of the first things you notice about this circuit is that the LEDs are in opposite ways around. I did that because the H-bridge reverses current, so one LED will light up when the motor should be running forwards and the other will light up when the motor is running backwards. We have our 6 volts, which is basically going to be the voltage coming directly off of the Omnibot's battery. Off in the corner here, we have what looks like just kind of a spare 3.3 volt doing its own thing. The reason this is here is we're going to be using this to trigger the inputs on the 1645. Now, this is the same voltage that's used by the BeagleBone's GPIO pins. So long as this works, we should be able to successfully drive the chip using the BeagleBone. So basically, when I take the 3.3 and I short it to one of the inputs, one of the LEDs will light up. When I put it to the other input, the other LED will light up. The data sheet specifies that if I put both inputs high or both inputs low, the IC is going to go into braking mode, which basically means it's not going to output anything. When we build this test circuit on a breadboard, we wind up with something that looks a little bit like this. These two orange wires are connected to the in1 and in2 pins on the chip. So basically, by taking my little 3.3 volts and connecting it to here, one LED comes on, and here, the other LED comes on. Based on this, we know that we're using the chip properly. It seems to be working as advertised. But there's one little problem. When I took my ammeter, which measures the amount of current something is drawing, and I put it between the 3.3 volt line and the inputs on the chips, I see that it's drawing around 10 milliamps. That might not sound like a lot, but 4 or 5 milliamps, depending on which pin you're using, are the maximum current draw for the BeagleBone. So I had to go back to the drawing board, and I did this. Basically, all I've done to the circuit is I've added these two transistors. For those of you who fell asleep in grade 10 electronics, a transistor is basically a switch. What it lets us do is kind of the same thing as a relay. We can control a lot of current using not much current. So now, instead of connecting the 3.3 volts directly to the input pins on the chip, all I have to do is connect it to the base on the transistors. Here is our updated breadboard. You can see the two transistors in the front, and a quick test shows that when I connect this and this, everything is still doing what it should. Unfortunately, I didn't shoot any footage with the ammeter because I only have so many hands, but when I put this version of the circuit on it, barely even rocked the needles. So next week, when we hook this up to our BeagleBone, we should have no problems, and more importantly, won't wind up reducing our nice little credit card-sized computer to a useless, smoldering hunk of plastic. I'm Japo, thanks for tuning into the Tommy Project, and I'll see you next week.